Relation between focal length and radius of curvature. So, let us try to derive the relation between radius of curvature and focal length in the case of both mirrors. One is concave mirror, the other is regarding your convex mirror. So, first of all, let us try to understand something regarding the convex mirror. So, convex mirror means, for that we have to consider a large sphere from which a portion of this mirror is being cut . If it is coated outside, this will become a concave mirror, and the same thing, any portion, any side you can consider. For more clarity, I am trying to discuss the other side. So, small portion of the mirror is being cut, and suppose out of which, if the mirror is coated inside, a portion of the mirror sphere, hollow sphere is being cut. If it is coated outside, inner side will be the reflecting surface, that will be your concave mirror, and the same mirror, a portion of which is being cut and it is coated inside, then the outer surface will be the reflecting surface, and this mirror will be our convex mirror. So, let us consider both the cases and discuss in detail. First of all regarding your convex mirror. In the case of convex mirror, first of all, let us try to consider the principal axis. So, this is your principal axis, and this is your pole of the mirror P. Pole of the mirror be indicated with the letter P. As we know that all the light rays that fall on the lens, those light rays which go straight and fall on the mirror, after reflection will be meeting at the focus. Suppose if the mirror is being produced, then the center of curvature will be formed somewhere here. So, this is actually your position of your center of curvature. The center portion of the complete mirror itself is called as center of curvature. All the parallel beam of light rays, say AB, after reflection from the curved surface will reflect back. These light rays, after falling on the curved surface, will reflect back, and if they are produced, then they appear as if they are meeting at some point, and that point we generally name it as F, and where C is the center of curvature. Suppose all the light rays that are falling straight ahead on this mirror, perpendicular to the mirror, will definitely meet on the center of curvature C. So, this indicates the normal drawn to the surface. So, this C will indicates the normal drawn to the surface. So, all the parallel beam of light rays that are falling on AB will be reflected back and taking the path as BD. AB is an incident light ray and BD will be a reflected light ray. But this BD, if it is produced inside, it supposes as if it is meeting at a point F. and for this curved surface a perpendicular drawn to this always meets at a center of curvature. Any circular part, if you consider, okay, any light ray that is moving perpendicular to this will be meeting at the center of curvature. So that is the normal drawn to this surface N. Now from the figure it is clear that the portion, this is the angle between the incident ray and normal is called as your angle of incidence, and the angle between the normal and the reflected light ray is generally called as angle of reflection. And from the laws of reflection we know that angle I is always equals to angle R. Condition from the laws of reflection. Angle I is always equals to angle R. Now let us suppose that these rays are produced ahead. When these rays are produced ahead, we observe that these two are parallel lines and this here is an intersecting line. These two are parallel lines and this is an intersecting line on that surface. So based on that we can consider that, let us name the picture as something like this. Let this be angle 1 and here be some angle 2. From this picture it is very clear that angle I is equals to angle R. The reason for which these two are intersecting lines. If this happens to be R, this must also be equals to R because of vertically opposite angles. So clearly angle R is equals to, I name this as some angle 1, angle R is equals to angle 1. Reason for this is vertically opposite angles. Vertically opposite angles. So two conditions we have observed from the laws of reflection. The angle between the incident ray and the normal I is equals to the angle between the normal and the reflected ray, that is R. So I is equals to R. Also from this, NC and FD are two intersecting lines, and from this picture we can find that angle 1 is equals to angle R because they both are vertically opposite angles. Now one more point is that if you produce the AB line ahead, then we observe this AB line is parallel to the principal axis. If two lines are parallel and this NC is a intercepting line for this AB and BC. So then this is these two lines and this is a intersecting line. So here we observe that this portion is I, then this portion here which is equals to 2. So this is the line here, bottom line pink one here, this is a corresponding intersecting angle. So here if this happens to be I, then this must happens to be 2. Okay. So these are the two lines we have considered. Observe the picture carefully, children. So this line indicates these two lines and this is your correspond intersecting angle. Here if it happens to be I, here is your I, and here it is given as 2, so here it is 2. So clearly as the given two parallel lines and it is an intersecting line, angle 1 must be equals to angle 2. The reason behind this is why angle 1 is equals to angle 2, because they both are corresponding angles. They both are corresponding angles. So I is equals to R, R is equals to 1 and 1 is equals to 2. So from this we can conclude that since R is equals to 1 and 1 is equals to 2, we have I is equals to 1 is equals to 2. So this indicates that this one is I, children. So I is equals to 2. Sorry, this is I is equals to 2. So I equals to R, I equals to 2, R is equals to 1. So equation 1, 2 and 3, instead of I can take R, and instead of R I consider it as 1, angle 1. Instead of I consider R, and instead of R I considered it as 1. Similarly, instead of I also I considered it as 2. Instead of I can take it as 2. Again, instead of I can consider it as 1. So from these three laws condition, we observe that angle 1 is equals to angle 2. Angle 1 is equals to angle 2. From the picture we observed that angle 1 is equals to angle 2. Whenever in a triangle two angles are equal, then the opposite sides must also be equal. So observing the opposite sides, we can conclude that the opposite sides of angle C is FC. Angle 1, opposite side of angle 1 is FC, must be equals to opposite side of angle 2 is equals to, from here to here, this is B and here it is F. BF. FC is equals to BF. Suppose if you consider that this B is very close to point P. If you consider this B as very close to point P, then the aperture will be same. Then instead of B, if B is very close to P, instead of BF, may I write it as PF? So that is a condition. If B is very close to P, so instead of BF, I can write the same as PF. So BF is now replaced with PF. So from equation 1 and equation 2, I can conclude that since FC equals to BF and BF equals to PF, we have FC is equals to PF. FC is equals to PF. So this means these two values are equal. But we know that from here to here, the length from focus to principal axis, pole of the mirror, we represent it as F, focal length, and from center of curvature to pole, we represent it with R. So from figure, we observe that PC, this PC can be written as PF plus FC. PC can be written as PF plus FC. But we know that PF is equals to FC. So instead of FC, I can replace with PF. So PC is equals to PF plus FC is again written as PF, or PC means from PC, P to C, this total distance itself is named as your R is equals to 2PF. Let me write it once again. PC is equals to 2PF. P to C will indicate with the letter as R, and P to F we represent with F. So hence F can be equals to R by 2. So the relation between the focal length and radius of curvature is given as focal length is equals to half of the radius of curvature. So this is an important relation, children. So the relation between focal length and radius of curvature is F is equals to R by 2. So what we have considered is we have to consider a convex mirror and a principal axis through which a light ray AB is incident, and this light ray AB is incident after falling on the convex mirror reflects back and takes the path as BD. So AB is your incident ray and BD is your reflected ray. A normal is drawn to this surface, and this normal definitely intersect at a point C. From the laws of reflection, so angle of incidence is equals to angle of reflection. So I is equals to R, and also from the picture we consider that the value of R is equals to angle 1 because of vertically opposite angles, and also angle I is equals to angle 2 because they both represents the corresponding angles. So from these three laws we conclude that since I is equals to R and R equals to 1, I can be taken as 1. Here I can be taken as 2. So since I is equals to 1 and I is equals to 2, we can conclude that 1 is equals to 2. Again from the picture, we see that since both angles are equal, angle 1 is equals to angle 2, their opposites sides opposite to the opposite angles are also equal. So the side opposite to angle 1 is FC and the side opposite to angle 2 is BF. So FC is equals to BF. And if you consider that for a small aperture, small sized mirror or a mirror with a small aperture, the B will be very close to P. So instead of writing BF, as B is very close to P, I can even write it as BF. So for very close to P, or for a case of small aperture, for a small sized mirror or for a small aperture, so as BF can be written as PF. Okay. So from 1 and 2 equation, if FC equals to BF and FC is equals to PF, we can conclude that BF is equals to PF. FC equals to BF and BF equals to PF, we can conclude that FC is equals to PF. Now if you observe the picture carefully, we can write that this PC can be written as PF plus FC. PC can be written as PF plus FC. But just now we wrote that instead of FC we can replace it with PF. So FC is replaced with PF. PF plus PF indicates 2PF. So PC is equals to 2PF. From the figure, from P to F, pole to focus indicated with the letter smaller focal length, and from pole to center of curvature indicated with the letter R, radius of curvature. So naming those, PC can be written as capital R and PF is replaced with F. So the relation between radius of curvature and focal length is taken as R is equals to 2F, or F can be written as R by 2. So this is the relation between the focal length and radius of curvature in case of a convex mirror. Let us try to prove the same by using a concave mirror. So let us go look at this. Case 2 regarding the concave mirror. Let us consider a concave mirror as shown in the picture, and let this be a principal axis. Okay. Let this be a principal axis. Any light ray that is falling parallel to any light rays that moves parallel to the principal axis will reflect back as shown in the picture. So let us go through that. The light ray AB that moves parallel to the principal axis, this is the incident light ray, after reflection will meet the principal axis at some point called as F. Imagine a normal drawn to this, a normal is drawn to this mirror. Whenever a normal is drawn to this mirror, the normal drawn to the mirror meets the principal axis at a point called as your center of curvature. So this is your normal, a perpendicular line drawn to this surface. So clearly from figure, this AB is an incident ray and this BD is a reflected ray. AB is an incident ray and BD is a reflected ray. The angle between the incident ray and normal drawn to that surface is called as angle of incidence, whereas the angle between the reflected light ray and the normal drawn to this is called as an angle of reflection indicated with the letter R. Okay. So now let us produce this value, and if this is I and this is R, let us name this angle as some angle 1. Let us get some relation between angle 1 and angle R. Here we go. From the laws of reflection, we know that angle I is equals to angle R. From laws of reflection, we know that angle I is equals to angle R. Also, if you consider this, we can conclude that these two lines, if you observe the two lines carefully, if you produce the line AB and this is the other line CF, it is produced, they both will be parallel to each other, and this will be your intersecting line. NC will be your intersector. These two parallel lines and NC is your intersecting lines. In this, we can conclude that angle I must be equals to angle 1 because they both indicate your corresponding angle. So, these two are parallel lines and this is an intersecting line. So, clearly from picture we have angle I is equals to angle 1. Angle I is equals to angle 1. Reason for that is they both are corresponding angles. So, from the two relations we can conclude that since I is equals to R and I is also equals to 1, we can conclude that angle R is equals to angle 1. So, in this triangle, we observed that two angles, that is 1 and R, both are equal. So, if two angles are equal, then the opposite sides of those angles are also equal. That means this implies that the opposite side of angle 1 is this value, that is BF. The opposite angle for R is your CF and the opposite angle for 1 is your BF. So, CF must be equals to BF. CF must be equals to BF. But if you consider for a small aperture or a small sized mirror, BF will be very close to the pole P. This is your pole. So, for a small aperture mirror, instead of B will be supposed to be coinciding with P. Small aperture mirror means B will be coinciding with P. So, instead of BF, we can replace as B is coinciding with P. So, BF can be written as PF.